Good morning, everyone. Welcome to our NMIS Insights webinar today on the Advanced Forming Research Centre and FutureForge. If you don't mind bearing with us just for a moment to allow attendees time to connect. Thank you. Good morning, thanks for your patience and welcome again to our NMIS Insights webinar on the Advanced Forming Research Centre and FutureForge. I'll just now pass you over to the AFRC's Chief Operating Officer, Helen Lightbody. Thank you.
Thank you very much, Debbie. Good morning, everybody, and a very warm welcome to the Advanced Forming Research Centre webinar. I hope you'll find it an interesting session and it's going to generate some really good discussion for you. So I'll just share my screen. What's up? Hopefully everybody can see that now.
Yep, that's perfect.
Lovely, thank you very much. So before we start, I'm going to cover some housekeeping guidelines with you. As Debbie said, the webinar is recorded. It's going to be recorded and it will be on the NMIS YouTube site later on today. Because of that, your microphones and webcams will be switched off while the presenters are speaking. If you've got questions as coming up through the session, if you could use the Q&A tool, put all of the questions into that, and we'll run a Q&A session at the end of the presentations. If you'd like to carry on the conversation on social media, then please use the NMIS hashtag. And there's going to be a survey at the end to capture any feedback on what you think's gone well and what would make these webinar sessions even better. So I'd be really grateful if you wouldn't mind to take the time and complete the survey. Today's webinar will cover a very high-level view of AFRC, how it fits into the NMIS group, and then the team are going to share a more in-depth look at our core capabilities of forging and incremental technologies, sheet forming, and materials and residual stress. The AFRC is here to facilitate the government's industrial strategy, and our mission is to translate innovation into products, processes, and technologies, such that the UK metal manufacturing community can use these to address their production challenges. We bridge the gap between the universities and lower TRL research organisations, whose remit is more about developing and proving concepts, and then up to industry who want to qualify and operate production systems. Our partners and our customers face a number of challenges. So first of all, product challenges, that they want better, more sustainable products with higher performance, but they've got the added business challenge that they want those products at a lower cost, faster production times, and with a higher return on investment. And then the final challenge is really around the process itself, and being able to turn the black art of forging and forming into a science through data-driven manufacturing. Being able to extract data throughout the process, analyse it and interpret it in real time, and allow us to better understand forging and forming in practice, giving us the information to help predict and control processes and material performance in the future. And this particular aspect is a key part of our FutureForge project and is a driver behind our digital twin vision. So you can see from this picture here that the AFRC opened its doors back in 2010 with only 12 staff. By 2014, we had doubled in size, both in terms of headcount and in building size. And with the completion of our FutureForge construction of our FutureForge facility back in 2020, we increased in physical size again. So back in 2018, Scottish Government announced the 56 million National Manufacturing Institute Scotland, with Strathclyde as the anchor university. And today the AFRC is just one of the specialist centres that sits within the NMIS group. Today we've got 80 staff across 3 teams, supporting production scale equipment in our workshops and our labs, and delivering a wide range of research projects for academia and industry. This particular slide shows you the core elements of the AFRC, with the Advanced Forming Research Centre the Lightweight Manufacturing Centre, the Digital Factory, and the Manufacturing Skills Academy. They're all currently in place and working, and in actual fact, the new NMIS building is under construction and will be due to complete in September next year. For anyone who doesn't know, the National Manufacturing Institute Scotland is a group of people, facilities, and capabilities that are led by industry and are being brought together to enable Scotland to become a world leader in advanced manufacturing. And as a group, the NMIS's objectives is to address the challenges faced by manufacturing businesses of all sizes and in a number of sectors, increasing productivity and competitiveness at a local and a national level. And in order to support that endeavour, NMIS will also work in developing the supply chain, all the supply chain links and the available skill sets that businesses will need to move forward in this future of manufacturing. NMIS is very much a collaborative venture, so it's operated by Strathclyde University, but supported by academia, industry, and the wider public sector. And you can see from this particular slide who our key stakeholders are, including Scottish Government and Scottish Enterprise. And we're one of the 7 high-value manufacturing catapult centres and the only one in Scotland. I'm joined this morning by my team leads, who are all senior knowledge exchange fellows from Strathclyde University. It's Dr. Aster Conway, Dr. Evgenia Yakushina, and Dr. Salah Rahimi. Each of the team will cover their research areas in more detail. So I will introduce you first this morning to Dr. Aster Conway, who will talk about our forging and incremental technologies. So over to you, Alistair.
Thank you very much, Helen. I'll just share my screen. Just let me know when you can see that.
Yeah,
That looks fine.
So thank you very
Oh, you've gone on
much,
mute.
Helen. Sorry. Thank you very much, Helen, and welcome everybody to this webinar about the AFRC. I'm going to talk to you about the forging and incremental technologies at the AFRC, which is a team that I've been leading now for a number of years, and it's been quite a growth area within the centre. So forging incremental technologies, effectively, this team has actually been running since the start of the AFRC in 2009 with our first bit of equipment, which was the screw press that we brought into the centre. Since then, we've invested over £25 million in this technology area, covering a range of different processes and a range of different capabilities. We've developed robust capability in the process development and optimization in forging and solid state near net shape processing. Our remit is really to work directly with industry and academia to demonstrate the benefits of some of these more novel and advanced processes and to address the fundamentals of deformation behaviour of materials, the prediction and control throughout the processes, and fundamentally improve processing routes for industry and manufacture. And to do that, we're able to provide a unique range of manufacturing solutions from industry. In the next couple of slides, I'll cover off some of the research and development we do, and then I'll talk a little bit about one of our bigger programs, which is the FutureForge program. So firstly, to talk a little bit about research and development into solid state near net shape manufacturing. So this is a processing group that we've been developing within the centre or working on in the centre for the last 6 or 7 years. We're focused on net or near net shape processing routes, which allows us to get up to 80% improved material utilisation when you compare it to more traditional methods like forging and machining operations. A lot of the processes are termed as lossless, i.e. in the processing route, there's no reduction in material, there's no removal of material or reduction of material volume from the input. So whatever material you put into the process is what you get out in terms of the volume. And through a lot of these processes, we can see increased mechanical properties such as improved fatigue, increased material hardness and more localized material hardness, which can be controlled, and also some grain refinement, which also has some mechanical strength property improvements. The majority of the processes are done in a cold condition, so a lot of the cold working properties that we see through these processes do have a significant advantage. The processes themselves are very high accuracy and control, so we can achieve up to 0.1 millimetre wall thickness in many of the processes, and also 0.2 of a degree of a cone angle. So it's very high precision, very high accuracy processing. But fundamentally, the reduced processing time compared to conventional machining is significant. You know, we've gone from, in some processes where you've got a large machining time of hours or even days, we've taken that to less than 10 minutes in some cases. So significant processing time reductions with these near net shape process routes. And that also leads to things like 60% reduction, up to 60% reduction in energy costs. It's a more leaner value stream. So that's a lot of the aims and why we're trying to, you know, develop all of these near net shape manufacturing processes and the key benefits. To give you an idea of what we have in the center, I've got a few videos there to show you. So on the left-hand side, we have cold flow forming, where we're starting with a forged and machined preform in a cup shape. We're locating that onto the spindle. That spindle is then rotated round, and 3 roller tools are then brought in to incrementally deform the material over the mandrel. And again, that is a cold process, so there's no active heating in that process at the moment. And what we're able to do is extrude that material out and to create things like shafts, long tubular sections with that high accuracy wall thickness control, and also achieve up to 2-3 times the preform starting length. And again, it's a very quick process compared to traditional methods where you're forging and machining a shaft. The middle video shows another variation on the incremental forming called shear forming, where you're starting with a plate material, so a flat disc. Again, it's located onto the spindle, and in this case, the roller tool comes in and shear forms or moves the material up that conical section. This video is actually real time, so you'll see how quick the process is at creating some of these conical shapes. You can see examples of some of the typical components on the right-hand side there in the bottom. And again, it's done in a cold condition. So it's a very, very quick process to achieve conical shapes. The third video you can see over there on the right-hand side is our second flow forming machine. It's got a vertical orientation rather than horizontal of our first machine. And it allows us to do other types of components, smaller, more intricate components, and do internal features and things onto the parts. The part that you're seeing formed there, again, started life as a plate material. It's spun over into 90 degrees and then it's flow formed down, and there is actually some internal features at the bottom of that part as well. So it's a very intricate process. It's a very flexible process, and because it's done in a cold condition, allows significant hardness and mechanical property improvement. Some of the other near net shape processes that we have in the center are rotary forging, which you can see on the left-hand side, which is another incremental deformation process. This process is a competitor to traditional forging, whereby instead of having a large tool set and a single hit process, you're incrementally forming that material over to create flange components, discs and rollers, again in a cold condition. It's a very novel process that we've been developing in the center. We've got a very intricate bit of equipment which can do up to 90 degrees nutation angle, and it's a very flexible piece of equipment as well. On the right hand side, we have our latest bit of a kit that we've brought in for incremental forming, which is a radial forging equipment. So many of you may be familiar with this process. We've been developing the process modeling around this and also understanding the materials evolution for these processes. You can do it in hot or cold condition. And as you can see, some of the applications that we have there are transmission shafts and other shaft components with internal diameter changes and also external features that we want to put in. Moving on now to some of the forging we've been doing within AFRC. So AFRC and Strathclyde as a university, we recognise that forging is a key process within the manufacturing supply chain. And I guess our facility was set up to help demonstrate and understand the fundamentals of forging of materials and link that base with production scale equipment and demonstration validation equipment. As you can see on the right hand side, one of our bits of kit, and I'll talk about them in a couple of minutes as well. Our aim really is to work in partnership with supply chains, develop leading processes and technologies to facilitate high integrity, low cost and short lead time production. Some of our forging operations you can see there in the graphic. So we do hot and cold forging of bulk, precision, and obviously near net. The industries range from automotive, aerospace, energy, and oil and gas, all of whom we've worked with and we have a good customer base with. And the materials range from titaniums to steels, nickel alloys, and also magnesiums. So we're very up for trying different materials. We're keen to work with our materials team to develop new material grades and understand how these materials can be applied to traditional forging operations. In terms of the kit that we have for forging, again, we've got a significant amount of production scale equipment. Starting at the top right-hand side, we've got our 2,100 ton forging cell, which includes a 2,100 ton screw press, a 1,200 degree rotary furnace, a clipping press, and also some automation equipment, which has got a pick and place gantry mounted robot, which allows us to do up to 70 kilogram payloads, and also a die lubrication spray robot, which allows us to vary the patterns for dagging of the dies and understand the effect that that may have on the process. Next door to that, we also have the 500 ton servo drive upset press, which has got a 500 ton vertical load and a 315 ton horizontal load for doing heading and extrusion operations. As it's a servo driven press, it has variable upset and clamping stroke, and it allows us to control the velocity profiles very accurately as well. And that's a process that we've been developing a lot of understanding around the materials and, again, the process modeling of. We also have some lab-based research presses, a 25 ton hydraulic press and a 100 ton hydraulic press as well, which is more for the sort of fundamental material research elements that we do within the centre. And as well as that, we have a 500 ton hydraulic press used for bulk and sheet forming. And these are all supported by a range of different furnaces. So we've got three furnaces at 1200 degrees, 750 degrees and 1400 degrees, which we use for our processes. We also have the rotary furnace, which I've mentioned already. And then we also have a large scale 1 meter cubed gas furnace, which we use for dedicated research within the centre. So it's a wide range of forging equipment and ancillary equipment we have within the centre. I'll now move on to one of our latest investments and one of our biggest investments we've made in the centre on the FutureForge programme. Some of you may have heard of this previously, and there is a separate insights webinar for the FutureForge that you can find on our YouTube channel if you want to know a little bit more. Fundamentally, FutureForge is a very ambitious programme which brings a tri-modal 2,000 ton hydraulic press with a gas and electric furnace and also a high accuracy manipulator to allow us to accelerate the validation capability and provide a validation platform for high integrity forged components. It's a £21 million investment funded through the Aerospace Technology Institute, ATI, Scottish Enterprise, and also the University of Strathclyde. So it's a significant investment for us and a significant capability that we're developing. In terms of the press itself, as I said, it's a tri-modal press for a 2,000 ton hydraulic press, and it brings three modes of operation into the one platform. So we can do open die forging, closed die forging, and isothermal forging in the one platform, which is very unique. And it allows us to have that flexibility to look at these three different modes of operation, but also to trial and understand how the materials behave and these very different processing routes. In terms of the technical capabilities, so the hot forging platform has a high accuracy manipulator. It has two industrial furnaces, a gas and electric furnace, and it also has digital data capture, connectivity and security, which we'll talk about in a couple of seconds, and high temperature die capability. An open die, we can do 1,200 tons, closed die up to 2,000 tons, and isothermal up to 2,000 tons. And we can process a 1 ton billet within that open die capability. So there's a range of components that we can do and a range of different materials that we're developing for use within the platform. So as you can see from the name, FutureForge, it's not just about the forging, it's all about trying to understand how we can take the forging aspects into the 21st and 22nd century as well. So it's a state-of-the-art platform for data gathering, connectivity, as well as the actual forging. So it allows us to digitize the hot forging and allow us to test and validate that within this platform. It combines obviously the three forging modes that we have with some of the existing capabilities we have in the centre: material characterization, residual stress, which my colleague Sala will talk about in a few minutes, and also our metrology and our modelling expertise to allow us to understand better understand the subtleties of each processing method and provide a very predictive method of forging. So it allows us to improve the forging predictive power, explore less intensive or energy intensive methods, and basically accelerate the development of the high integrity forged components. I recognise that that's quite a lot to take in within a few minutes, so I have my contact details there if you want to contact me, and also be available for questions and later on in this session. Thank you very much for listening.
I hope that everyone could see my screen as well.
Yes, that's fine, Evgenia.
Perfect, thanks, Laura.
No problem.
So I will continue the story of the AFRC, and it was a brilliant introduction made by Helen. Thanks very much. It will save a couple of minutes for my presentation. But as you know, the Advanced Foreign Research Centre, we are the part of the National Manufacturing Institute Scotland, and we are globally recognized centre of the excellence. We offer world-class expertise in majority of the cutting-edge technologies, and we are supporting different companies to develop the solution, which help us to bring the real benefits for their business. So the next slide, I would like to share with you how we are working and who we are. Today, I'm representing the forming team of the AFRC, and equally to the materials and forging and incremental technologies team, we're one of the oldest team in our family. We are mainly working on the bridging the gap between different TRL levels, and we are trying to bring the academic expertise from the people who are awarded with the PhD and bring them to the same basis where the people from the industry sharing their experience. Therefore, we are bridging the gap between the academic knowledge and the industrial requirements, which is one of the most painful and most needed areas of the research and the industrial experience as well. And in the next slides, I will be sharing with you what we are doing and how we are doing our research. As you can see on the left-hand side diagram, the forming team represented by 4 different themes. And that helps us actually to cover the whole variety of the inquiries, which is usually coming from the industrial or the academic partners. We are representing our expertise in the hot and cold sheet forming, but at the same time, taking into account how many different aspects of these processes need to be taken into account and what type of the questions need to be answered. We are providing the expertise also in the tribology and the surface engineering questions, which is one of the most important aspects when you're speaking about the sheet formability and sheet forming processes. But another area of the expertise, which is strongly supported by our team and provided to our customers to support their business, is modeling. And we believe that it is a key component to grow up the company and sector's productivity. In order to give you an insight what we are doing in our team, we are looking to the not only to the development of the manufacturing processes, but actually helping customers to improve their current manufacturing capabilities and use their current assets in order to fulfill to the new manufacturing requirements. We are working on the exploration of the new opportunities from the innovation and always very open to consider the new innovative process and how it could be quickly developed and applied for the manufacturing needs. We are looking up state-of-the-art manufacturing technologies, and we are associating this with the current business challenges. But therefore, we are going through every single step of the process if it is required, and we are facilitating, we are delivering and planning manufacturing technologies. But this is the one of the exercises which is answering the most painful and the most important question for some of the customers, how through this assessment and analysis we could de-risk the investments in the new technologies. And as a few examples, how we are working with the industrial partners and how the industrial collaboration supported from the AFRC expertise and background. We are working on the industry-driven project, but at the same time, we are providing the extensive knowledge of the industrial processes. And at the bottom of this slide, you could see a couple of different scenarios, how the industry engagements examples performed in the forming team and in the AFRC. So one of the scenarios, which is actually we are starting from so-called closed loop analysis, and we are looking for the characterization of the material. And based on the data generated over there, we are developing material and process models that actually helps us to make the first go right. And then we are coming to the process validation, which actually allows our customers to get their solutions, to get the solution for their problems in the very cost efficient and very productive manner. At some cases, customers are coming from the different background, and they are more looking for the tooling side and development of the tooling questions. And that's also one of the expertise which we are holding in our team. Another area of the expertise, which is one of the most helpful and one of the most needed type of the service which we are providing in the team right now and in the center. We call these methods of manufacturing assessment, and I will speak about this a bit more on the next couple of slides. The other very useful and quite required type of the communication is when we are sending our engineers and they are walking through the line at the company side and try to identify every single step of the manufacturing process which could be optimized. So we are finding the solution for the current issue, for the current manufacturing capabilities, which could address the significant improvements and benefits for the business. And at the same time, the diversity of the knowledge and expertise allows us to work actually from the far ends of the process, when the customer is basically coming with us with the tool and saying that I would like you to develop the manufacturing process, which is a totally fine. And we are starting from the points which is the most comfortable for our customers and clients. And on the next slide, I would like to speak about the one of the main capabilities which sits within our team. The superplastic forming and the superplastic forming capabilities in the center, representing quite a broad expertise that have been developed for more than 10 years already. We are starting in 2010 when the AFRC have been initiated, and we start developing the assessment of the testing capabilities to understand material process parameters and material properties in order to fulfill the superplastic forming requirements. In 2013, the 200-ton superplastic forming press have been installed in the AFRC, and we called it a small SPF press, as it allows us to do the first level of the assessment of the real type of the superplastic forming condition for the small type of the components, and at the same time develop the full modeling capability and assessment to be ready to go for the full scale. And in 2014, we scaled up our capabilities to the 1,200-ton superplastic forming press that have been installed in the AFRC by that year. And it allows us to do the full-scale manufacturing trials for the superplastic formability assessment from a variety of the materials. We are quite comfortably working with the several titanium alloys, as I will be speaking as I will be covering at the next couple of slides. And also, we are looking for such materials like magnesium alloys as well. And for the current stage, we are actually proudly could say that multiple large-scale superplastic forming programs now performed on the very broad level in the AFRC, been undertaken and actually completed with a total value over 10 million. But speaking about the other expertise represented in the forming team, as I said at the very beginning, we are quite comfortably covering the wide variety of the sheet forming processes with regards to all temperature ranges, including hot, cold, and warm sheet forming process. As you can see on that slide, we are actually covering the processes which could be found as an applicable in the industrial sectors associated with aerospace, defense, and automotive. And therefore, we have a good diversity of the processes that will answer the needs of those sectors. I'm pretty sure that Sal will cover our testing capabilities, which is actually allows us to understand all the material parameters required for sheet forming processes. But we started our story from one of the very innovative and very flexible forming process called an ISF. And at the bottom of the slide, you could see that there is a complex shape part that have been formed in great collaboration with our Boeing partner. The part have been formed in the room temperature condition for high strength aluminum alloy, which was quite a great achievement at that time. But we haven't stopped at this, and we decided that we have actually to develop the set of the forming process that could be represented by the AFRC. And we looked at the deep drawing and cold and hot warm press forming process that allows us to cover the next level of the needs from different customers and businesses. We moved to the next level as customers always coming to us with the questions, how you can form these high strength materials, how you could achieve these complex shapes. And you need to address your requirements and your capabilities to this type of the questions. Therefore, we moved for advanced forming capabilities and jumping from the 3-axis to 5-axis CNC machines, and formed quite a complex shape profile from the titanium components in the room temperature, which was a good achievement. And again, our Boeing partner was quite pleased with the outcomes and results. And jump into the current facilities and current capabilities of the foreman team. We are looking to the warm rolling processes in order to develop the hybrid multi-material for the lightweight sheet application, which is one of the required areas by the quite a few industrial sectors. And we also look into the hybridization of the process, which actually represents that from the CNC machine, we've been able to modify it to the laser metal deposition and use the heat assistance in order to support the ISF trials. On this slide, I would like to give you a brief overview about our modeling capabilities. And I hope that you can see the diversity of the process which we've been covering through our expertise and knowledge. You can see at the bottom side of this slide that we are working on the SPF process modeling, as well as for single and multi-sheet type of the components and optimization of the process parameters. We have been quite succeeded in the forming, in the superplastic forming and modeling all of this process for a new alloy, which have been a challenging partner for the Thai for usually widely used for the superplastic forming type associated processes. The hydroforming is another area of expertise where you could see the representation from the experimental modeling and validation stages. And on the bottom part in the center of the slide, you could see a beautiful example, which is actually representing the way how the forming team within AFRC collaborated with an SME called Cruiser's Wheels. And we've been working on the computer fluid dynamics analysis in order to understand what should be the design of the water wheel that could be then installed in the countries such as South Africa in order to generate alternative energy sources. The thermal analysis and another modeling modeling of the processes, such as deep drawing, is also covered by our expertise. But in the last couple of slides of my presentation, I would like to spend a few seconds speaking about the methodology, which is actually called methods of manufacturing assessment, which allows our customers to have a very successful process down selection. This simplified diagram actually covering quite a detailed and in-depth analysis when the customer is coming to us with the needs of understanding around the potential materials that could be used and swapped with the current analogs. What type of the product, what design, what type of the manufacturing processes could be used for these needs. And then through the ranked analysis and evaluation through the weighting factors agreed with the customer, we are coming to the development stage where we are assessing the ROM costing for comparative assessment. At the end, customers are able to actually identify the most optimal solution in terms of the manufacturing process, which will be the most financially de-risking option for them. And that's quite a flexible process, but at the same time, it's given quite a lot of varieties and in-depth understanding of the all requirements and parameters. And the last slide for my presentation today is basically highlight the vision and development plan. In the forming team, we are, as I initially mentioned, we are quite openly looking to the innovative process, and we are now supporting and facilitating the activities which is answering the needs of the lightweighting, resilient UK manufacturing, and net zero resource efficient manufacturing as well. And on the right-hand side, you could see a couple of the processes and ideas and solutions which we found quite required and needed by the customers from the different sectors. And through this ideology, we're hoping that potentially in the next 10, 20, or 50 years, the solutions that have been developed through the forming team in the AFRC could be found in the air or driven through the road. Thank you very much for your attention.
Excellent, thank you everyone. So I just want to share my screen. Are you able to see my screen?
That's fine, Salah.
Excellent, thank you. So just continue with the presentations. My name is Salah Rahimi. I lead the materials and residual stress team. In the next 10 minutes or so, I will take you through our capabilities. Should you have any inquiries following this presentation, please get in touch through my email, which is on the screen. So my presentation would include a brief introduction and an overview of the materials and residual stress team's capabilities, activities, and vision. And to take you through a little bit of more details, I'll I will present a few case studies just to give you a better idea on what we do, and hopefully there will be some time towards the end for a discussion. So materials and residual stress sits within the heart of the AFRC's research. It covers 5 major areas of materials testing and characterization: materials modeling, fundamental materials, or what is written here as material science, welding and joining, primarily focused on rotary friction welding, and residual stress measurements, modeling, and control. All of these are in support of forming and forging technologies, which you have already seen through my colleagues' presentations. So the purpose of our activities in the materials team is basically to design better materials, high performance materials at reduced cost. And that's through identifying critical length and timescales through different characterization techniques, covering micro to macro, and using a variety of different techniques. And based on those analyses, we tend to bring multimodal information from a region of interest and then spatially correlate these together to be able to predict materials mechanical behavior and use it in modeling and prediction in support of different types of forming and forging technologies. So our primary goal and vision is to become a center of excellence for materials research in support of manufacturing, especially forming and forging technologies, be able to predict the generation and evolution of residual stress throughout manufacturing processes. And this is, of course, the main ultimate goal is to lead and develop and deliver 21st century transformational design and make processes to revolutionize the future generations of products, as you have seen some of them throughout the previous presentations. So basically, residual stress and materials science is underpinning every single technologies within the AFRCs, all the forming and forging processes, and pretty much cuts across all the processes. So there is a mutually relationship between the techniques and the characterization methods and the output of our research with any of the forming and forging technologies. Basically, the purpose is to create a joint research ecosystem to accelerate computationally led discovery and maturation of the material system. And our flagship project, as Alistair mentioned earlier, FutureForge, is one of the programs that we really want to integrate all the materials capabilities and integrate it into a larger scale, industrial scale process models to be able to predict materials behavior and manufacture them in a more sustainable, efficient way. So what we do within the materials and residual stress team, basically we are focusing on metallic materials primarily. More than 90% of our activities is focused on metallic materials. We try to find the relationship between materials properties, microstructure, and the processing routes in order to be able to predict and optimize those processing routes. So our characterization techniques cover advanced materials microstructure characterization, thermomechanical testing from room temperature to over 1300, and strain rates of 10 to -6 to 500 per second. And we have a quite good suite of residual stress measurement techniques that I show in a second. And also we do quite a lot of research with like displacement and strain mapping and generation of forming limit curves for sheet metal forming. So our residual stress capabilities include a variety of techniques, including non-destructive ultrasonic and X-rays, semi-destructive hole drilling based on strain gauges and electronic spectral pattern interferometry, and larger scale, fully destructive techniques such as contour method and slitting methods, which I'll show a couple of examples later on. So the first case study I'm showing is about modification of microstructure of titanium throughout manufacturing processes. Titanium 6-4 is one of those materials that is heavily used in the cold part of the engine, or the areas of the engine that the temperature is not quite high. This material requires to have a globularized microstructure, as you can see on the bottom right-hand side of the screen, to resist all those demanding conditions. However, during manufacturing, achieving that microstructure is quite a challenge. So we in the AFRC trying to understand the evolution of microstructure, how to get that globularized microstructure from a lamellar structure or as-cast structure in the most efficient way. So you can see on the left-hand side a few examples of a really large sample size or comparable to industrial scale, where we have forged them and then we model them and slice them, look at the microstructure evolution, compare it with the actual measured microstructure in order to be able to create a model to represent those behaviors. So more detail, and now we've done more detailed analysis, such as looking at the microstructure with EBSD and trying to reconstruct the prior beta grinds at elevated temperatures where the microstructure was before cooling, during forging, before cooled down to temperature, to room temperature. So in this case, we can link the evolution of microstructure at the high temperature beta condition, where then we know how to control the microstructure evolution by changing the process parameters. So next case study is on residual stress. For those of you that do not have, are not familiar with the residual stress, I'm sure you have seen its sign in your kitchen. A nice example of residual stress is like cutting watermelon that basically cracks ahead of the knife or cracks on its own. This is due to the heterogeneity in basically the difference in mechanical properties between the skin and the flesh. Basically, the skin wants to contract while the flesh wants to expand, and then if you introduce a crack, i.e. cutting it, it starts to grow on its own. So this actually exists in nature pretty much everywhere. Like all of you have seen cracked carrot, or if you open a rhubarb, it will bend. So this exists in pretty much in every material, and it's actually one of the challenges during manufacturing. As you can see in this example, where a part has been halfway quenched through water purposefully just to generate residual stresses by heterogeneous cooling. The half in water cools down quickly compared to the half in air, which cools down slowly. Then we have cut that, measure residual stress by cutting it halfway through, or contour method, and measure the surface profile following the cut. And what you see in after the measurement, this is the surface profile you see, which is actually a significant difference between either side, where the changes in the cooling rate resulted in residual stresses of different magnitudes. As you can see, the top contour plot shows the stress distribution, and the bottom plot 3D image is like exaggeration of the change in the sample geometry, i.e. the way residual stress wants to change the part. And in fact, that's similar for other parts. Like for instance, if you quench a disc horizontally, the residual stress wants to bend the disc, as opposed to vertically, where the residual stresses wants to twist the part. And imagine these changes the manufacturing processes. So if a technician wants to machine these down with the same methodology, the final part it results in distortion, i.e. different final geometry, which needs to be taken into consideration for manufacturing of high value components. So in the AFRC, we want to predict and model the generation and evolution of these stresses right from the beginning up to the final machine part and create a digital twin of these processes. Of course, at this stage, we are only able to simulate. Creation of digital twins requires artificial intelligence and decision making. However, that is part of our activities, especially when we have the FutureForge operational. And finally, the last case study I'm going to show is our rotary friction welding. Essentially, rotary friction welding involves a part being spun at high speeds and pressed against a stationary part, where a joint will be made between the two sides. The right-hand side image, it shows you one of the rotary friction welding machines. We have the 300 tons rotary friction welding machine we have. It's a giant machine. You can see a box on the bottom of the image just to compare how big it is. So we do modeling and prediction of the process, also advanced characterization of the process, taking into consideration materials model to understand how the microstructure evolution happens. In this example, for instance, we have predicted the temperature evolution and compared also the shape with the final welded geometry. You can see that the formation of the flesh and the geometry is pretty much the same in a low alloy steel. So we use these information to optimize our models. For instance, in this case, we have done a advanced analysis of the microstructure, where we characterize the microstructure by EBSD, and using EBSD data, actually, it is possible to reconstruct the prior austenite at the temperature, i.e. where the temperature was during welding at elevated temperature above AC3 temperature, what is known as the austenization temperature, where the whole microstructure was austenite. And then using a crystallographic orientation relationship, we can reconstruct those grains. In this case, I've used Kurgimov-Sachs crystallographic orientation relationship to reconstruct the prior austenite grains, and use the texture in the prior austenite grains to understand the deformation mechanisms during the rotary friction welding. For instance, looking at the microstructure and looking at the texture history of this, it is possible to know what temperature the material was at, what was the dominant deformation mechanisms during welding, and on that basis, you can then understand how the whole deformation, micro deformation mechanisms are, and actually use it as material subroutine for a large scale FE analysis. And finally, obviously, we want to combine multi-scale information to create multi-skills and multi-physics based model and data analytics using new algorithms, and hopefully by the development of AI, artificial intelligence, we will be able to scale up the technologies we have and kind of make the fundamental science more relevant.
Sorry, we seem to have lost connectivity with Salah there.
Yeah. He was nearly at the end of the presentation anyway. Do you want to give him to see if he comes back, or should we start the questions, Debbie?
Yeah, do you want to start having a look at the questions, please, Helen, and see if Salah can join back in?
No worries. Okay.
Thank you.
So thank you very much to the three speakers there. That was three terrific presentations. There's, oh, is that Salah back now?
Yes, he is.
Apologies, I don't know what happened, but
No.
that was the final slides anyway.
Okay, are you finished then, Salah? Is that okay?
Yes. Yeah.
Thank you.
Thank you very much, Salah. I've actually got a question here for you first, if we can cover this one. It's from Andrew Johns. The question is, can residual stress reduction be applied to machining processes as well as forging and forming processes?
Well, very good question. You quite often I receive this question, so hopefully I can explain it very quickly. The purpose here is not to reduce residual stress. So unfortunately, you cannot reduce it because the determining factor is achieving a microstructure, which is one of the criteria by all industries to satisfy the final mechanical performance, like resistance to fatigue, crack, stress, corrosion, cracking, creep, and so on. So unfortunately, to achieve those right microstructure, residual stress is often a byproduct. So instead of like trying to get rid of it, we must find a strategy to control it. So our purpose here is actually to control it, and controlling it throughout machining is one of the research area we are actually doing in the AFRC, using residual stress as an input for like for FE simulation. It is possible to design a machining strategy to reach a final component.
Thank you very much, Salah. Andrew, hopefully that answers your question. We've got another one from Nitesh. Do you also use neutron diffraction to measure residual stress?
So as you might be aware, Hitesh, neutron diffraction is a large government scale facility. It is not possible, unfortunately, to have it like in a lab. So it is possible to submit a proposal to neutron diffraction facilities. There are quite a few of them around the world. Well, actually, it's wrong, not quite a few of them, maybe 3 or 4 of them around the world. And upon the successful application of the proposal, it certainly is possible to use neutron facilities, as we have done it ourselves here in the FRC for several times.
Thanks again, Salah. There's one question in the chat that's already been answered, but just for the benefit of everybody, the question was from Andy Loudon, and Andy was asking if we've used flow and shear forming with polypropylene sheets. Wanted to say that primarily our work has been in metallics with nickel alloys, aluminium and steel, but it is an area that we'd be interested in having a discussion with. So, and Alistair has given Andy his contact details. If anybody else would like to be involved in that discussion, please let Alistair know, and his contact details are in the chat function.
I think just to add to that, Helen, as well, I think any material which has got a relative amount of ductility, maybe an elongation of about 12% minimum, you know, that's the kind of material we're looking at for these kind of processes where there's a severe plastic deformation being generated. So it depends on the material, but that particular type of material is not something we've done in the centre, but as a research organisation, it's something we're always interested in looking at what the possibilities are.
Thanks, Alistair. Not seeing any other questions in the chat or in the Q&A. Is there anybody that would like to unmute their mic that would care to ask a question live? Not seeing anything. Okay. Salah talked earlier on about the research life cycle or the research ecosystem, and there's a question that actually might bring that out. So if somebody had come up with an invention but couldn't find a UK supplier for materials, the AFRC would be able to help them decide on the best way to make the product and find a supplier. Evgeny, is that something that you would like to just touch on, and how that process would work and how we would use the ecosystem?
Yeah. Well, I think that Salah beautifully covered the representation, how the ecosystem should work, but with regards to the different scenarios, how we can work around this, There is always an opportunity if we are looking at the brand new material, which actually have to be developed to fit the purpose. So we have some certain requirements in terms of the strength, ductility, or fatigue life. And it obviously will be a certain requirement for the chemical composition. So that should be done in the one scenario where we are looking for the current manufacturing facilities around the globe, either it is local Europe or the worldwide, and trying to fit the requirements that have been performed by the customer in terms of the properties and how the current manufacturing facilities could answer these questions. Another one scenario is when customers is actually looking for the innovative material, but for already known products or the known process. And in that case, we are acting on a slightly different manner. So we are comparing the analogs of the materials and using the knowledge base and database which exists in the AFRC, we are able to have a high level prediction on the very quick rate in order to suggest a couple of the options, a couple of the variants that could be considered as a first startup, as a first point for the consideration. And then through the next level of the investigations and understanding of the material properties and requirements, we are able to refine these requirements versus the material or the product type.
Lovely. Thank you very much, Evgenia. Still not seeing any more questions. So given that we've got 4 minutes left, I think, Debbie, if we just wrap it up, my final thanks to the three speakers. Thanks very much, team. And thank you very much to everybody who's attended the webinar.
That's great. Thanks very much, Helen. Thank you. And as Helen just said, thanks very much everyone for joining us today. Hope you enjoyed today's webinar. And thanks also to our speakers from the AFRC, Helen, Alistair, Evgenia and Sala. And as Helen mentioned earlier, shortly after the webinar closes, we'll send out a survey to you, and we'd be very grateful if you could take a few moments to complete it, as your feedback does help us shape future webinars. We have an NMIS Insights next Wednesday on the 2nd of June in collaboration with Rolls-Royce on Rotary Friction Revolution, and you can find details of this on our website at nmis.scot. Thanks once again, and we'll just bring the webinar to a close. Thank you.